Well, we're looking at maps. But we can play on that. Okay. It's not like made all of this. I made. Wait, just move right here. That way, universe right here. No, that's okay. Oh, wait. This is really. This is my wall. Oh, wait, no,
All right, guys, we can get started. Okay, guys, let's get started. All right, so in the first half today, all right, so, all right, guys, so all right, so in the first half of today, I just kind of went over the syllabus, right? Answered any questions you had. We talked a little bit about like the history of it, just kind of terminology and things like that, right? So now I'm more formally going to start going over the topics, okay? So the first thing that I like to do is what I call word problems. Okay, so we'll be doing that. You will get a homework assignment on these word problems. So I create usually like 5 word problems every semester, and you have to solve it, right? That doesn't require any coding or anything like that, but it's actually, I think, really important, okay? So I'll show you basically, by example, what you need to do with these word problems, but they're really important, okay? So the idea is we're gonna think of a problem, and then what would we need? What are the things that we need to define clearly so that we can then start solving this problem, right? So, how do we build the model and everything, collect the data and so on, right? So those will be the word problems. I'll do that, and then probably towards the end of class today, I might just show you a little bit of Anaconda just so that you can install it at home and then practice replicating what I do in class so you have a sense of what to expect, okay? Our environment, the Jupyter. I'm sure a lot of you have seen Jupyter notebooks, but I'll kind of show you, some of those very basic things. It should take a few minutes. And then we'll do maybe 1 or 2 tensor operations, which is what I usually refer to as. I don't like to call them linear algebra problems because then it's misleading, right? We're not doing linear algebra in this class, but we are using tensor operations, which is a matrix multiplication, which is a formal concept from linear algebra, right? So, and you will have some problems of that later next week. I'll give you some problems for that. Okay, does that make sense? Yeah. All right, so yeah, so today we're doing word problems, a little bit of Anaconda, and just a little bit of code examples, and then next week we'll do more and probably start building our first neural network, right? Something, like a temperature or something like that. Okay, any questions so far? All right, so let's get started. All right, so what do I mean by word problems, right? So word problems, as you can see, I have my whiteboard here and a pencil, and these problems you solve like that. You'll take a sheet of paper, pencil, and you need to start, coming up, answering basically questions, right? So it's like a template that I have of, what are these things for this problem? What are these things for this problem? And so on, okay? So the best way to understand this is to look at a problem, right? So I just have some problems here, and do that. All right, so basically the homework will be like this. You can expect about 5 of these problems, and you'll just have to do, for each one, you'll have to answer these questions, okay? So for the following problems, identify and or define the following. The X matrix, the Y vector, what are the samples, the classes, if they exist, define a set of features, define the dimensions of X and Y, and indicate what they mean. This is really important because a lot of the time, regardless of what data, what problem you have, you basically call your data X and Y. Okay, so that's a common practice. It's good to have like these templates of how you solve machine learning problems, right? You always want to understand what everything means in the code. So we're going to refer to our data as the X matrix or the Y vector, okay? And that's going to, so right now, even in the word problems, even though we're not coding them, we are defining them as X and Y. Then when you start coding your solutions, they will be called X and Y. They'll be variables of the same name. Make sense? Yeah. All right. So we need to define what these things are, right? What is the X matrix? And notice in something that I mentioned here is this idea of dimensions. Define the dimensions of X and Y. That's actually really important. Whenever you do something with neural nets, with PyTorch, when you're defining these models, a lot of the time you're going to do something where you do print dot shape. And what that means is you're constantly looking at the dimensions of your things. That's one of the, mastering that skill is one of the most important things you can do with neural networks, okay? You're not going to be inventing new CNNs or new transformers or GANs or a simple multi-layer perceptron. Rarely do you do that, right? Or you won't be doing that. But the one thing you will be doing is creating these tensors, right? These matrices and vectors, and you need to know what these sizes are. What that means is how many rows does it have, how many columns, because all that has meaning in machine learning, right? That is one of the most critical skills for you to understand. And I do recommend also that you pay attention to the terminology and use it correctly, right? So that everybody knows, if you mean X, that's something, that's your data, right? And when you refer to the columns of X, that means something, and the rows mean something. For instance, the rows are going to be our samples, always, okay? And our columns are going to be the features, always. You shouldn't call the columns of X anything other than features, okay? Does that make sense? So we're going to get into this idea of trying to understand these templates. And then this X and Y, whether you're building the temperature conversion function, or you're building a GAN or a CNN, it's always the same, right? It has the same meaning, okay? And then, obviously there's going to be abstractions on top of that, but you always start with that. It's almost like it's really nice because you might do a lot of work, a lot of code or whatever it is, just to arrive at a really nice X and Y. And then that X and Y, then once you create that, you know that a lot of the code you already have will work if you just created it. So it's basically about taking any problem and putting it in a specific format. And then that format will feed in nicely into your code. Do you see what I'm saying? So you almost have, think of it as having this toolbox of code examples. They always take in X and Y. So if you have a new problem, put a lot of work into creating that X and Y, and then it'll just feed smoothly into the algorithm. Got it? Right. So that's kind of the idea. So let's see. So basically, I create these problems, right? So there's problem 1, a classification model for detection of electric vehicles while on the road. That seems like a pretty complex problem, right? It's not straightforward. It's not solved by any means. And I just wrote one line here, but that can be a lot, right? So that's the other thing with these word problems. There is no real right or wrong answer. You just have to identify, make your assumptions on how you're solving it, and then make sure that the terminology is correct. That's what I'm looking for, okay? When you submit your homework assignment, I will look at the problem, your assumptions, and then how you define these parameters, and then just, assign the grade based on that. Got it? You understand? Okay. So really, that's what we need to understand. So another problem might be a model for predicting the age and breed of pets in a veterinary clinic. Right? So that's also, how does that work? A model that identifies if a patient in the ER is having a stroke. Okay? So a lot of these problems, actually, you could argue that you could use a camera, right? In a lot of these, you could have a camera looking at the patient, a camera looking at the pets, a camera even in the car, right? But there's other sensors also, not just cameras. There's like, oh yeah, sorry. A what? Vitals? Okay, yeah, like sensors, yeah, that's true. You're right. Exactly. Exactly what I was saying. So you could think of just using a camera, or you can think of using vitals, right? Like these watches that people have nowadays. And that can be multimodal also, if you make that decision that you're going to actually combine the image data with the sensor data because you think that's going to give you better results. You see that? So the problem is whatever you want it to be, what I'm really looking for, you can keep it as simple as you want. That's perfectly fine. But I just want you to define X and Y correctly for your problem. Okay, that's really the key. Make sense? Got it, guys? All right, so let's do one of these and let's just start thinking through how we would solve them, okay? And then, like I said, later on, not this week, but next week, I will give you a set of problems, 5 or so, and you'll just repeat the same exercise, okay? All right, so let's start with the veterinary clinic, okay? So number 2, a model for predicting the age and breed of pets in a veterinary clinic. Okay, so you have to start thinking about the place, right? It's a small clinic. Veterinary clinics are usually small, right? 20 people or less. You got dogs, cats, but the breed of them, is it a German Shepherd or is it I don't know, some other Cocker Spaniel, something like that, right? So this is what you're trying to do, right? So that's the idea, all right? So then you have to answer. So now I'm going to X, Y, what are the samples in the classes? So I'll start writing that down in the whiteboard. Okay, so what is X? Right, what is X? What is Y? Oops, sorry, yeah, sorry. What is Y? Okay, what are the samples? What are the samples? Okay. What else? The classes, so the breeds, right? Define a set of features, define the dimensions, okay? All right, so a model for predicting the age and breed of pets in a veterinary clinic. So first of all, it's saying the age and the breed, okay? Age and breed. So what is age for a pet? Between 0 and like 20 years, right? In general, that's age. That's a number, right? Okay. But breed, okay, of cats and dogs. So German Shepherd, Doberman, what's another dog? And then cats, right? What types? Tabby cats, Siamese cats. Do you get where I'm going with this? Right? So you have to think about this problem, right? So how do you do it? So the secret is, I'm giving you like the secret sauce here, right? And so the secret is just actually figure out this X and Y and maybe the sample when it's not obvious. Okay. Also, you need to figure out the medium. So we need to define that. So what's the medium here? Like, how do we collect the data? We're in a veterinary clinic. We're building a model, some automation for whatever reason. It doesn't even matter why, right? But for some reason, we want to figure out for a pet the age and the breed. Do we need to define if it's a cat or a dog first? What if it's a ferret? So you need to make some assumptions, first of all, right? So let's limit the scope. Let's start there. So do cats and dogs. Yeah, let's do 2, right? So cats and dogs. So that's the first thing. If you want, you could also do just cats or dogs. Just state that in your assumption. I'm just going to do dogs. Okay. So what is X? So the first thing we want to look at is X is always going to be an N by M matrix. Just think of it as an Excel spreadsheet, rows and columns, right? That's what a matrix is in this context. Okay. So it's an N by M. And then that's going to be our X. Right here, X. I'm going to always use uppercase, even in the variable. In the program, it's going to be an uppercase X. And then my Y is going to be a vector. And this can change, but for now, to keep it simple, it's going to be an N by 1. Do you see that? This is really important, right? That this, you're starting to like restrict your approach to solving machine learning problems, okay? No code, but this will be very helpful later on, okay? So now what the model is going to do, the model is going to, I'm going to denote the model as just a circle with M, and the model will take in usually X and give you Y. Do you see that? This is going to be we're going to call it a function or an architecture or the neural network or my machine learning model, whatever you want to call it. You can think of it as just a function. Takes in X and produces Y. Do you see that, guys? That's basically what we're going to do all semester. This simple little relationship, okay? And we're just going to learn a lot of complicated ways of creating this through code and everything and so on. But anyway, so for your problems, if you don't remember what to do, just start here, okay, for every problem. So we're trying to make a model of detecting the breed and the age of the pets in the veterinary clinic, okay? So N is going to be the rows, and usually this is going to be the samples. I'm just going to write here, these are the samples. Okay, and then these are going to be the features. So what are features? Features are descriptors of the sample. And each sample has to have the same exact features, okay? Same exact feature. So you have to also, I believe that's one of the questions, what are the features? I want you to actually think about the descriptors for your pets, for the pets. So in this example, in this example, defining the sample is easy. What is a sample? It's the one thing, right, that you give to the model and it predicts something about it. That's a sample. So in this case, what's a sample? If we're trying to detect breed and age, what's a sample? Each pet is a sample. Do you see where I'm going with this? So some are pretty obvious, right? And then others, as you will see, I'll make sure they're not, right? You have to then define it, like you have to like drill down, okay? But, trying to predict the stock market, I may give you one of those. You have to try to think about it in terms of this, okay? But this is very helpful, right? So to know how to solve these problems. So you have a sample. Okay. Okay. Right, great. So you can answer the question, what is the sample? You can say the sample is a pet. Now, obviously you can't just give a pet to the model. You have to give some digital thing of the pet. So what do we use? You can pick whatever you want. So what's a good medium? An image, maybe? Do you want to go with an image, or do you want to use something else? That's sorry.
Weight, height, color.
Okay, so you want, like, somebody would look at a pet, have a little like survey and fill out. We can do that too. Yeah. So that's another approach. So the nice thing about an image is you just give it the image and let the model figure it out, right? It could work with enough computational power. A simpler thing might be like we used to traditionally do things where we would try to extract things from the image or from the pet. So that's perfectly fine. So let's say that the features are going to be, these types of descriptors, right? So features are going to be things about the pet. So how many things do we need? It's hard, right? But this is what you have to think about when you do a machine learning problem. What are the features that describe, and if you select good ones, then it's going to be a good model. You could select really terrible ones, right? And then the model won't work. So it's usually about the features, okay? Data is king. Just because you have a transformer doesn't mean that it's going to be good if you have bad data, right? Okay? So which features did you say? I'm sorry?
Weight, height, color, face shape.
Okay, so weight, height. So you have to, okay. So weight, height, color, very furry, not so, right? Those kinds of things. Exactly. So do you guys see? Right. So I don't need you to write like 40 features, right? So just do 4 to 5. You thought about it. And then based on that, decide, okay, I would need about 20 to 40 of these, right? You make that call. It's entirely up to you. Does that make sense? Okay. So you've defined what the features are. How are you getting these features? Probably a person would go in and fill those into maybe a computer, right? So they have a computer, a form, and they're just going to enter. Okay, the dog weighs so many pounds. The height of it is this with a ruler and so on. Enter that. The color of it is brown. And then, the fur, those types of things. And you enter it into the system. So how many features do you think we could collect like that? Just a number, any number. 1,000, 10,000, 20? Yeah, go ahead. 9. Okay, very precise, right? 9, and that's fine too. That's totally okay. That's what I want you to do, because you're thinking about, you're trying to rationalize this problem and you're going to break it down into something that makes sense, right? That you can actually do. All right, so 9 to 20. Okay, so we have this number, and the great thing about this is this number defines our letter M. So let's go with your idea. We've done a lot of research and analysis, and we decided, I think these 9 are the best. Now, are they really the best? We will know once we start running the experiments. There are ways, in fact, that machine learning will tell you if your features are good or bad. So that's another advantage. But for now, what's great about this is we've defined that we have 9. So remember that one of the questions in the word problems is, once you've defined X and Y, you want to define the dimensions of X and Y, right? So you want to know what number that is. So then we can go back. And so over here, this X matrix, we can already define the number as 9. Do you see that? That's it. Now, next question. How many samples will you have?
9.
Not 9. 9 is the number of features, right? We've defined that already here, the number of columns. So how many samples reasonably do you think you could have? 100, 100, 1,000? A million is probably too many, unless you own all the clinics in the world, right? So that's what you have to think about sometimes, right? So if you're Facebook and you're dealing with images, you could probably have a million, right? You have to think of it that way. But in this case, you have to think realistically of how you would approach this problem, right? That's the whole goal of this exercise. So you said 100, right? There's nothing wrong with 100. I would say probably try to collect more, because the more you have, the better your model is going to be. And it also depends, this is a difficult problem actually, because there's a lot of breeds, right? I mean, I'm not just saying, tell me if this is a cat or a dog. I'm saying, you know, what breed of cat, what breed of dog. So we have to think about that problem as well. Do you guys see that? So you have to think about it. But we already know that X is what? 100 by 9. That already gives you a lot of information. Why is that important? Because your neural network, some aspects of your neural network are going to depend on these numbers. You see what I'm saying? Like when you start defining your neural network, you will need some parts of it to be 9. Okay? Really important. All right, so this one then, the Y vector over here has, well, N, right? So that means there's 100. Notice that for every sample, and a sample is what? Let's say a row. Let's say I'm slicing row 2. That is what you would call a vector in the machine learning vocabulary, okay? So, you know, we have basically a matrix. If we slice out row 2, that is a vector, which is actually a sample, right? It's a sample of an animal, right? A pet, and the vector is of size 9. And this is really important, okay? And that's the key thing that you have to master, is these shapes. Any questions? And then on this Y vector, which is a column vector, you can also slice with index 2, right? And what that's going to give you is a row in this vector, right, that corresponds to this vector. What the model needs to do is it needs to learn to correlate those 9 features to whatever this is. Do you see that? You see that? Correlate these two. Okay, that's what the models do. Make sense? Okay. So we've defined that this is 1 for now. So what that actually, we need to predict 2 things that are different, right? We said we wanted to know the age and we wanted to know the breed of the pet. So now we kind of have to think about breaking that up a little bit. So should we create one model that gives us all of that? Or would it be easier to create 2 models? And one model gives us the age, one model gives us the breed. What do you guys think?
One model is both.
One model that gives both? Okay, that's a harder model, but we could do that. Yeah, go ahead, please.
You could have 2 sets of models for both cats and dogs, assuming.
So would you say a model that tells you if it's a cat and dog first, and then based on that, then it goes to the next model to give the breed? Yeah, you can do that. You can do whatever you want. Right, exactly. So if you want to do it that way, that's fine. State your assumptions though, and then just answer the questions, you know, the dimensions. Do you guys see this, how it works? All right, so that's basically the idea. So now we know that a sample is a pet. We know that the X matrix is 100 by 9. We know that the Y vector is 100 by 1. Okay. But that we need to break that down a little bit more. So let me see here. I think I'm going to move to a new page. I think this is what does that. Oh, yeah, that page. There we go. I have a cleaner page here. All right, so now I'm going to go to the pencil. X 100 by 9. But let's start with predicting both at the same time. So that means that this would be 100, possibly by 2, right? So you would have 2 columns. One column would be for the age. Okay, so you have a pet, and this one is 7, this one is 3, dot, 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 this one is 10. Do you see that? On the other end, we have the breed of the animal. How many breeds do we have? You also need to define that. The more you have, the harder the problem, okay? So we can just constrain, let's say we have dogs, we have cats. So how many? Just define them. 10 dog breeds and 4 cat breeds. You see that? So then that's a total of 14 classes possibly that you would have. See where I'm going with this? So then, okay, I'm just quantifying this. So there's 14 breeds. It's a difficult problem because you're mixing cats and dogs, but I mean, it could work. Like if cats were always blue and, you know, dogs were always yellow, it would be an easy problem, right? So that can happen. So here I have column 1, column 2. And so this one we said was for age, and then this one we said was for class, okay? So here we have another problem. But for now, we're just gonna use, we need to have some way of representing the classes. So in machine learning, you don't give words to the models, okay? Okay, even if you see a software that somehow takes in like strings, like letters and words, it's converting it to a number, right? So on the simplest representation, we're gonna represent every breed as a number between 0 and 13, because there's a total of 14 classes. Do you see that? And then there's problems with this approach, but I'm just taking the simplest approach that I can. Okay, so then I'm gonna say breed 7, breed 3, breed 6. Now keep in mind, this 7 does not mean the same as this 7 because they're on different columns. Do you guys see that? That's really important. This is also a number that it's predicting, like a 7 or a 6. It's predicting 1 of 14. Okay. Also, there's another problem. Just because something is a 7 and something is a 1, it doesn't mean that the 7 is somehow more than the 1. Do you see that? Where in this problem, that's exactly what it means. 7 is more than 1 because it's age. 7 here is not more than 1. It's just other. Okay. So machine learning here, if we do this approach, this is called a regression, like a type of a regression problem. If we do this one, it's called a classification. We still need to do something to make this easier for the model to predict. Got it? Everyone with me so far? Okay, so let's move to another sheet of paper. Okay, so I'm gonna now do this one here. So I've got my X, I've got 100. This was 9, remember? Each pet is represented. Length, height, weight, I think, color, and things like that. But we need to break this down. So now notice that I'm doing this. This is still 100. This is still age. Age. 37. Oh, it's not 37, sorry. I don't think a pet can be 37 years old. I've seen cats that are 18 years old. Okay, so 18, 8, 3, and so on. Okay? But the classes, they were problematic if we just keep 14 classes in one column. Because as we said, 7 is not greater than 3. They're just different. So a better approach is to do something called one-hot encoding. So you break, and this is really the approach that you should always take when you deal with something like this. So then now, what I'm going to do is I'm going to create 0 to 13 classes. Do you see that? For the individual pet classes or breeds, breeds. Okay. So now, instead of coding 7, right? What do? I'm just going to skip. I'm going to do like only even numbers. So I'm going to do like 2, 4, 6, 8, 10, and so on, right? I'm just skipping the uneven numbers, but they're still there. And let's say that the pet was class 8, right? That was the number 8. But the model, what you would do is, instead of writing the number 8 in one column, you now have 14 columns, right? And so this column here will have a 1. And all the other columns will have what? A 0. Very good. 0. Do you see that? And that's a much better approach to classify. This is, in fact, what we will do most of the time in classification, right? So we'll start seeing these simple ideas all the time. And this will affect the architecture of your neural networks. Okay? But it's good to be able to understand how to take these word problems and always break them down into this X and Y. My suggestion here would be that I would want to separate the age from this approach, right? So I would have this one column. I would have this one column as being model 1, and it's a straight up regression model, which we will learn later on. You know, we'll do examples of that, but basically regression is when you give it whatever input and it's always predicting a number or a set of numbers, etc. So something like the price of a house, the stock price, the age in this case, right? So we could build a model just for that, for the regression part. And then we have another model, call it model 2. Model 2 for the classification. Does this make sense, guys? All right. So anyway, this is the approach that I want you to take. So based on this, now you can say, what are the dimensions? So the dimensions of X are going to be 100. Sorry. The dimensions of X are going to be 100 by 9. That was pretty easy, right? To define. But the Y for this problem was a little bit harder. Sometimes you'll get problems where the X is really hard and the Y is pretty easy, pretty straightforward. So that's the whole point of these. We'll do different exercises where you're trying to break down your problem into this X and Y. And if you follow kind of this approach all the time, you'll be able to pretty much start solving any problem that you can think of. Okay. So that's the idea. So now Y, the dimensions of Y are going to be definitely 100, right? Because we always need a corresponding thing for every sample. But now we established that this was 14 plus 1. So in this example, it's 15. Although you probably want to break it down into 1 of 14 and 1 of 1. Make sense? Guys, any questions? All right, so these are the types of problems you will do. Let's go back to the Word document to make sure we covered everything. All right, so the X matrix we've defined, the Y vector we've defined. What is a sample? It's a pet. What are the classes? Well, not everything was a class. One of them was a regression value. And then we had another one that had 14 classes for the 14 breeds. Define a set of features. Somebody said 9 were the optimal, and then we kind of listed it out. Define the dimensions of X and Y, which basically brings everything together. Okay, got it? And so now, once you've done something like this, you can go to your data, start writing code, and generate this X and Y, right? And you create a CSV file or something with this data, and that's what's going to feed into your neural network model. Make sense? All right, great. So hopefully that made sense. So one more thing I want to do, although this is not a requirement of the word problems, is I want to show you the connection between this and the actual neural network. Okay, just briefly. So I've said that I'm going to build 2 models. Model 1, which is a regression model, and model 2, which is a classification model, right? Without writing any code, I'm just going to write that network architecture that I gave you in the beginning. So let me remember. So it's 100, 9, 15. Okay, I remember. So I'm going to create a new page. And now that I have that data, you do this architecture. You're an architect of the neural network, right? You're going to define the architecture of it, okay? So since I'm doing two models, I'm going to do model 1 first, M1, right? And it's going to be the classification problem of the 14 breeds. So what does that mean? Okay, the input of it is going to, I'm just going to write it down here as being this for now, like a little rectangle. And I'm going to say this is the input, okay? And then I'm also going to have for the classification model M1, so this is the 14 breeds. Okay. I'm going to have an output. And the output basically tells me what breed of animal it is. Make sense? All right. So because you know those dimensions, you can start to define this architecture. So we know from the previous slide, X is usually the input, right? And Y is the output. Okay, so we have 100 and we have 9, right? We have that. So we need to use that information to define our neural network. So 100 means 100 samples, and 9 means the feature, the descriptors of each sample, right? So maybe some of you already know. So how do we use that information to define this? Remember, this is the neurons, right? So it means, values of each sample need to go in here. So those are the features, basically. So because those are the features, that means that every sample, every pet goes into the neural network, right? Think of it as going in individually. But all these samples are of size 9. They're vectors of size 9. They're just these 9 parameters that we've collected. How much do they weigh? How tall they are? All that. So then this layer here is of size 9. Do you see that? And that corresponds directly to this 9. So that's why it's really important to get this X and Y defined, because then it starts defining everything else. Got it? All right. So let's go back here. So we've defined this one as being 9. Let me make that more correct. 9. Okay. What about the output? That's also going to be neurons. This is what we're trying to predict. We're trying to predict what? The breed. We had 14 breeds. So basically, and we actually have that like this. So we're going to, we give it a sample and we just want it to produce a vector. Let me see if I can use a different color here. How do I do it? There we go. Okay. So we want our neural network to always predict that vector. Not, a vector of size, what? What size is that? 14, right? And that vector should always give us a lot of zeros and then 1, 1. And that 1 should be in the place of the class that we are predicting. Do you see that? That's how it works. Okay? So that's really important. So the model is always trying to predict this one over here. That's size 14. So if I'm going to go over here, then now I know that this is 14. I've defined the inputs and the outputs. Make sense? For model 1 of the breeds. Okay. Follow-up question. So we know that X was of size 100, right? And that 100 was the number of samples, number of, whatever it is, right? Where samples for the training, possibly. Later on, once the model's trained, we predict on just one sample. We don't have to provide many, just one. Can work for 1, 10, whatever. So do we use this 100 in the architecture in some way? Do we need to? You don't need to. And that's something very nice about how these libraries have been created, PyTorch and TensorFlow. That's a parameter you don't have to define because they're made to work with 1 or 10 or 100 or a batch of 64 or 1,000 all at once. The only thing that limits is RAM memory, because you're loading a lot of data in there. Right? So we don't have to define the model. Once you write it in PyTorch or in TensorFlow, if you were using TensorFlow, the model would work whether you run one sample through it or 10 samples at the same time, etc. And we will see that later on in the code. But for now, of that X, you don't need the number of samples. Got it? Making sense? All right. So now the next thing is, because we're going to be doing mostly neural networks in the course. So what is a neural network? It means that all these neurons are somehow going to be connected, right, in some mathematical operation to produce a new value here. Just give me a second. And then, but also, I can create another neuron over here, and that's all the samples connected to it. And I just can do that again, and I create another one, and all the samples are connected to it, which means what this means right now is it takes these four, does a mathematical operation to produce one number. And that new number goes in here. And then in here. And then in here. How does it do it? It doesn't. That's the power of it. It will figure out the best set of connections. Yeah, Henry. Oh, okay. Yeah. So, all right. So you see how I created one, then I created two, then I created three. We usually will kind of like represent them like this, and this just means a layer, okay? But how many neurons can I have in there? Like, you know, I did one, then I did two, then I did three. I can just keep doing that for forever, basically, right? But the limit is going to be, once again, the RAM of the computer, right? That's going to be our limit. There's some rules of thumb. Here, this has 9 neurons, for instance. We know there's 9 variables in here. How many should we have here? More than 9? Fewer than 9? You got to experiment. There is no like set rule, you know, because every problem is different. But, you know, I would probably start with like 20 and just see what happens. I would probably try 20, then I would try maybe 7, you know, just to see what the results are. And that's where this is a lot of experimentation. You build these architectures, you try different things, and so on. Make sense? So all of this we will code. So let's say, just for the sake of argument, I'm going to add ... here. And now I'm going to say, you know what, let's do 30. That means imagine there's 30 neurons in there. That number will go in your code because you're defining the architecture. Now, let me change to another color. Okay. Now, oh, and then this had 14 outputs, right? Can we connect these neurons all the way to the output layer? Sure, you can if you want to. So what would you do now? I would do this, pretty long, that, and that. Do you see that? That's how it works. Then, again, you repeat that. So that one. That one. And that one, and so on. You just keep doing that, right? And once again, you just create the connections. You don't know what this operation is. We will see later on what this operation actually is. It's just a matrix multiplication. But these values, so you're taking, let's say this is a 3. There's a 3 in here, right? And then let's say this is a 1. So 3 times 1, 3. You see that? And you try it. And then when that model works, maybe it's really bad. So then what do? This is 3 still, but instead of this being a 1, make it a 0.5. So now 3 times 0.5, right? And it produces a value. And then that's still bad. So then 3 times 0.05. And oh, okay, that starts to work better. You see how that works? So you play with these parameters until you get better results. Okay, remember that your goal, though, initially, all these values, these are 14, right? It's a vector of 14 that initially let's imagine, let's break this down. This is the vector of 14. Initially, it might, I'm just going to use not decimals, but just whole numbers here, it could start predicting a 3, a 7, a 5, a 0.5, a 0.1, and so on, right? There's a value in there all the time. However, that's not what you're giving it to train. When you train it, what do you give it? You give it a vector of same size, but what are the values there? All zeros and a 1. Why? Because that's the real data. And the real data, we already established that it's the breed, right? Do you see that? So here, this is the real data. This is what the model is trying to mimic. It's trying to predict that. Does that make sense? So let's say this is a German Shepherd, right? So German Shepherd means that this is a 1 and the rest are zeros. The model starts to predict like this, but as you start to optimize it and improve it, what's going to happen? Eventually, this vector will start to look like this, 0.01, 0. Well, oh, sorry, no, that's the actual value. Hold on. So actually, this one would be, you would want it to be 0.99. Do you see that? 0.99. Why? Because it's the 1, right? And then the other ones, this is a 0. This might be a 0.01. This might be a 0.02. The point is, these are very close to 0, right? And only this one should be very close to 1. It may never be a 1, but it's just going to be pretty close to it. You see that? So that's what initially the neural network gives you something like this. As it improves, it starts to give you this because it's trying to mimic this vector, right? Because this is what we established the training data looked like. You see that underlined in red here. Does this make sense, guys? Making sense? Any questions about this? Yeah, go ahead. Yeah, I haven't done that part. That's a good, because I said I broke it down, right, into model 1 and model 2, right? So this is, hold on. So model 2 and model 1. So I actually decided to make 2 models. I don't like the idea of having regression and classification in the same. Got it? Just simplifying the problem. But good question here. Yeah. I'll address it in a second. Like the same model after the age and the classification one shot. I could make one single model that just, I mean, I could make this. So I could do lots of things, but I could do this. I could have made this be 15 with one neuron that gives me age. It's not what I would, you could force it, but I wouldn't recommend it. I would just recommend making 2 models. One that gives you the classes and one that gives you, it's easy to do. I mean, just 2 separate architectures. Okay.
I'm just thinking about like in real-time application, we need the space.
You need the space and real-time application.
Because if you are doing like XY.
But there's no, you can have 2 models though.
Yeah, but we are using the same data.
Yeah, you can, the same data. And it goes into one model and then in the other model. And then you get 2 outputs and then you can use it however you need. It's okay to have multiple models. Yeah? All right, great. Again, we're just trying to, think about, like we're reasoning about how to solve these problems, right? With some structure. Okay? All right, so yeah, so we did this one. Now, the last thing I'll say is, this is not a deep neural network because I just added one layer. I could have added more layers, and that just basically means that I'm going to create more layers here with more neurons, and the connections go to here, and then these, the result of these go into the next one, and so on, right? And we make it deeper as we want to. But in this case, I just did one layer. All right, so any questions about the classification, basically? Is it clear? All right, so now let's do the regression part, right? The same exercise with the same variables. So let's go back and think about it. So 100 by 9 right? And 100 by 13, and the age was just 1, okay? And we know ages go from like 0 to 20, right? You know, age of a pet. So we can go over here. All right, so how do we do this second model? This is going to be a regression model. It's a regression model. You've probably heard of linear regression, right? And that's when you were trying to create these lines. With this, you can have regressions that are not straight lines or like curves and, you know, polynomials or whatever, right? So that's all that means. So anyway, we're going to build the regression model for the age of the pet. So once again, we're going to have an input layer, an output layer, and some layers in between, right? If we want to. So just like we did before, right? We said that we had these inputs that go into the first layer, and we had to find that that's the number of features. So we had 9 of them, right? So for the age problem, is that the same data? No or yes? Yes, right? Yeah, it's the same data, right? But we're going to build a different model. So yeah, so this is going to be 9. So this is going to be, oops, sorry, what is that? Okay. Oh, yeah. Okay, 9. Okay. So 1, 2, 3, ... 9. So later on, as we start coding this, you'll see this. Now, what about the output layer? How many neurons do we need here? Just 1? Yeah, because it's a regression problem. Here we have a thing, you know, before we had a machine that has 19 options, and it just tells you almost like a probability that it's this one or that one, or the 19. But you can also build machines that just produce a number, any number, and that's called a regression, right? So in this case, for age, for instance, yeah, you can use a regression. You know, I have another problem called the wine quality problem, you know, and that basically can give you a rating of a wine, you know, from 1 to 20 or something. So there, sorry, but yeah, so here we're trying to predict the value, the price of a house, you know, what's NVIDIA going to, you know, what's the price of an NVIDIA share tomorrow or a month from now, right? So you have basically 1 neuron, and this neuron can predict any number. So let's do the exercise again. So before, you know, we have now a vector, only 1 neuron. So this will produce a number, and this number could be a 3 or a 7 or a 9 or whatever. It could also be 9.5, 9.7, right? Any number. Remember that the data that we're going to give it, though, is going to be the number 3. So the time that we give it a, you know, we give it a 3 and it predicts a 7, it's going to compare that error, right? And it's going to say, okay, these weights are bad. I need to try another set of weights. So then that's new set of weights produces a 9. It compares it to the 3, and again, it's a bad answer. What does it do? It tries another set of weights. The next set of weights gives it a 3. It compares it to that 3, success. Do you see that? So what does that tell you about that set of weights? That it's good. You see that? And so that's kind of how it works. So before, when we did this, remember, we would always give it a 1 hot encoded vector, and it was producing a whole bunch of numbers, but eventually it should produce 1 hot encoded vectors. Okay. Now we just it's like we have to be more accurate here with regression. Okay. But the model can do it. Okay. And so that's the idea. All right. So now we've defined the architecture. It has an input of 9, and this is an input of 1. Like that. That's the architecture. That's it. And you will do examples of this when you start building your regression models. Now, in between, you can define whatever you want. So for instance, in this case, I decide that I'm going to use 2 layers. Okay. 2 layers, hidden. We're going to call this one hidden 1 and hidden 2. This has 9 neurons. How many neurons do you have here? How many? Remember, what is a neuron? A neuron is the result of doing some operation with the previous neurons, the previous values, right? All of them, you do an operation, like a sum, right? And then that gives you a new value for this. And then you have another one, and it's the same thing. And we'll see that operation in a second. But you have this, that, and that. And I've done 2. How many of these can I can continue doing this again forever, right? And it's just limited by the amount of RAM that I have. However, is it a good idea to make it really big? Probably not. So how do you define how many neurons to use? Kind of have to experiment based on your data and your problem. Rule of thumb, again, I would probably try 20, try 7, see what happens, and play with it. Yeah, go ahead, man.
In a general, like each layer, like if you're, like, say if you're starting out with like, lots of neuron, like layer.
Yeah.
Big number,
Yeah,
right?
like an image.
Yeah, and say if you're, I don't know, classifying down to like 2.
Yes.
2 classes. What a general thumb would be to half each.
Yeah, I funnel it. Yeah. I usually, that's a rule of thumb that I think does exist, right? If it's a big thing like an image, funnel to something. It's almost like the idea, like, don't let it procrastinate. If you give too much room for the model, it'll like start thinking too much. Force it to be more efficient. Like if you have workers, right? Take away stuff so they're more efficient almost. I mean, I'm just saying, you force it to be more efficient, and then it finds solutions. So if it can, it'll find a solution. Okay? Because it's an optimization problem. So it's trying to get to the optimal solution. And there's a lot there, right? We will look at some of these ideas later. Okay? Make sense? All right. So we were just thinking, as I said, today is just terminology and doing these work problems. We're going to continue doing these work problems next week, but you will have a homework at the end of that week and just to do this operation. Okay. I may ask you to do even the neural network itself, but just like this, to draw it out. Now, again, let's just, for the sake of argument, provide the number of neurons. So I'm going to say 20. Okay. And as Henry said, since we are actually only predicting 1 at the end, let's funnel it a little bit. So that means 10. ... 10. Do you guys see that? Why do you think adding more layers helps? Like if you notice, what I mean is, notice the connection, right? So this is the input, and then it goes to here. And then in the previous example, I just jumped directly to the end. But here I'm going through another layer. So it's like this data goes to here and then here. And just give me a second. And whenever you think about data going into one layer, think of it as a transformation. It's a really important concept. That's why the transformer is called the transformer, right? All it does is it transforms the data. A lot of what we're doing is taking our data and it's like dropping things we don't need and highlighting things we do need. And then those things keep going through the pipeline, right? So what do you think adding more layers does? Like, how does this help? Oh, yeah, sorry. Mm-hmm. Yep. Yeah. I agree with you. Yeah. So one example might be like, I have a book, right? I have a book, a page in a book, and I take out that page in that book and I just take a marker and I'm just like highlighting these passages, right? And then only those passages go to the next layer. So the next layer, instead of looking at all the text like the previous one did, because the previous one did look at all those passages, but then you highlighted 3 of them. In the next layer, only those 3 are looked at. Do you see that? And then it makes like an assessment based on that. It may turn out that was pretty bad. So what does it do the next time? Takes the same page, but it highlights another 3 passages. Do you see that? And then those 3 passages make it to the next layer, and then it makes a conclusion. And so eventually it finds the right set of passages to give the result that you want, because remember, it's training, right? So whenever it runs through all the transformations, it gives an output that is compared to the real value. And then it uses that information to modify the weights. Everything is done through this operation of the weights, this transformation. Got it? Does that make sense, guys? All right, so yeah. So now the one thing I want to show you is this operation, right? So I keep talking about this operation of the weights. So let's think about what it is. So what I'm going to do is I'm just going to highlight one thing. I'm going to highlight like just that one. Okay, I'm just going to highlight this one as an operation. So let's go ahead and do that. Okay, everyone with me? Right, so let's imagine that I'm going to zoom in into just that part of it, right? So I'm going to go here, grab the pencil, change the color to red. So I'm going to keep it simple. I'm just going to do like iris or something like that. It's the iris data set. So I have 4 inputs, right? The sepal length, sepal width, petal length, petal width. Just take a ruler and measure it. That's it, right? And I have some values. And then I have this. So what does that mean exactly? What it means, this is X is usually the input data, right? So that's going to be X1, X2, X3, X4. You guys see that? Yeah. And then this one here is the neuron that is predicted, like it runs through and it produces a number. Where I'm going to call it hidden layer 1, 1. Because it's that layer 1 and then the first neuron. I'm only highlighting that one. And then I need one more parameter, which I haven't, I've only mentioned, but I haven't like denoted yet, which is the weights, which is going to be W1, W2, W3, W4. Everyone with me? So then what's happening here is that this is actually just a simple math operation where you do H11 equals what? W1, right? W1 times X1 plus W2, X2, exactly. And that's it. That's all that's happening there. And these are linear operations, right? So then W3, X3 plus W4, X4. Make sense? That's the operation that's happening. So what you're doing is you're taking your, let's say you're doing the 9 values or whatever, then you would have 9 weights, right? Those X's are always in the sample data. But what is W initially? When you're just starting to train the process, right? What are those W's? W1, W2, W3, W4.
Probably random.
Random values. They are random values, okay? You're literally just, you don't know what it is. But these weights are like the whole magic, the whole thing right there. And so you try them randomly. What happens? So the X's are given, you have random W's, it produces an H1. And what do? You compare that to class 1-1. And if it's a bad match, you try another set of weights, and then you keep doing that until the weights start to get better. Yeah, Henry.
And with random values and whatnot, you're guaranteed to find a local min, but not like the absolute min, right?
I mean, yeah, that's kind of the definition of it, although they're very good nowadays. They may never find a perfect solution, but they do get pretty close.
Just like what's your find?
Yeah, you're talking about the optimization process. So it depends on the loss function and everything. But yeah, you can think of it as something like this. And this is it's just an academic example, right?
I'll find one of them.
Yes, exactly. So because he's talking about how are things found. So there's an algorithm called the stochastic gradient descent, right? So that algorithm, we're getting way ahead, right? But if you randomly for one weight are here, it's gonna try to go down, right? And so the problem is it might get stuck here. So unfortunately, it never got to this one, because if it had gotten to this one, this would have been lower. You see that in
One of those would be
it
sufficient.
this might be good enough for your company. Yeah. I mean, if maybe this makes you $1 million, this would have made you 2 million. Okay. So, but $1 million is still pretty good. You know what I mean? So it just depends on whatever it is you're trying to solve. Obviously, your goal is to never leave any money on the table. So that's why everyone is so obsessed with this one, because it's an additional million or 100 million or whatever it is, right? Of your company. But anyway, what I wanted to talk about is this one, right? So we word problems, then we did a neural network. The neural network is actually a math operation such as this one. This is really important. And this is what PyTorch or TensorFlow and these frameworks are doing for you, okay? Remember, you don't know what these weights are, but by the end of training, those weights could be pretty good. Everyone with me? Elon Musk, I think it was Elon Musk. Yeah, Elon Musk in an interview said something pretty funny that about, you know how when ChatGPT first came out, everyone was all like, it's going to kill us, it's AI, whatever it is. And then he just said that, ChatGPT or transformers in general are just architecture, right? That somebody defined. And then there's a set of weights, right? That basically it's like, you can think of ChatGPT as just being, like this, right? Like that. That's the architecture. That's ChatGPT. Then you train it with all the data in the world and a lot of computing power. And then you have these 3 weights, W1, W2, W3. So then you have a text file, and that text file contains W1, W2, W3. That's ChatGPT. That's it. That's what you're afraid of. You're afraid of a text file with weights in it. You see that? So anyway, that's meant to be a joke. But anyway, that's what he said, and it's true, right? There's some architecture, and then they spend $10 million maybe, use so much computing power, so much data to find a text file with these weights that plug into these architectures. So I'll give you another point of discussion, right? So let's say that Noah here built a ChatGPT, right? Yeah. And by I got to keep it simple. So this is ChatGPT, right? So a neural network with just 4 layers. So he wants to share his ChatGPT with someone else. What's your name? Alicia? Manisha? Yeah, with Manisha, right? So he wants to share his model with you, right? So he trains the model. Okay, mind you, this is much more complex, but to keep it simple. So he's got W1, W2, W3, W4. He spent $10 million, 10,000 GPUs, all the internet, all the books in the world, and got that. And he wants to share this with you. And he's just like being like, all right, I'll share it with you if you tell me what to do. So what would you ask him? He won't give you the whole model. But what could you do to get what he has? The weights, that's all you need. So you need the weights. Okay, so let's say you say, give me the weights. So then Noah comes in, okay, fine, I'm going to email to you W1, W2, W3, W4, right? So he sends it to you. What do you do now? You have a text file of weights. You need to create that architecture, right? So what you need to create the exact same architecture. So go to Noah, can you tell me your architecture? He's like, sure. So then, okay, you go in. Boom. You can create that easily, actually. That's actually, hopefully in this class, you'll be able to do. But what you don't have is you don't have the weights. But once Noah gives you these weights, then you just plug them in, like you literally load them in there. And now you have an exact copy of his model. So that's called transfer learning. That's, but basically also what I'm trying to stress is that creating the architecture is actually straightforward. Getting these weights, the right weights, with all that power is really difficult. Make sense? Yeah. So anyway, so hopefully at some point I'll show you how to, it's easy actually. It's very easy to exchange the weights. But anyway, okay, so hopefully that made sense. We went over, some concepts that are important, right? Word problems, defining the parameters, defining a little bit of the architecture, and some additional concepts and operations. Okay, so I think this is a good stopping point. I'll stay for a few minutes if you guys have any questions. Next week, we'll just do a few more problems. I'll do some of the NumPy examples as well, and you'll have like your first assignment. But I'll do a few more of these. Okay? All right, so let's stop here for today. And if you have questions, please ask.